Good. So for starters, I have some reef pulling questions for you. I think I'm slowly but surely figuring out how this is done. Let me see. I know we want polling as opposed to quizzing. So I just have two quick questions for us to start out on. It's actually on older material. I don't think it even gets into today's stuff, but still not bad for, kind of a warm up, especially on a Monday. So my first question is, which of the following is an isomer of the compound shown in the box below? So I'll turn that on. And I would put it to you that one of those is definitely the best answer. And I'll let that go for maybe 2 minutes. So the way this will work is I have two questions, they'll each be 1 point, and you'll get the other 8 points just for attendance. It'll automatically tell me if you're here. Actually, that's a lie. I noticed that for reasons I absolutely don't get, some students, it will not register their attendance, but I can still tell you are here if you answered questions. And there even is evidence that even if you get both questions wrong, I think I'm still able to tell that you are here, because I noticed when I looked at this stuff over the weekend, I would see some people had a 0 and others it would say did not participate. So you see the person with the 0 got both questions wrong, but was there, so they should get 8 points. And similar to that, if some people would get 1 or 2 questions right, respectively, and their grade would show up as a 1 or a 2 because it didn't automatically give them those 8 points. Well, I try to flag that when I'm transferring the grades to my personal grade book and then finally onto eCampus. So it's like I said, whatever you see on eCampus, which may take me a couple days or a week in order to get updated, whatever you see on eCampus supersedes whatever you see on the REEF website. But if, with this many students, things are gonna fall through the cracks. So, if you see your REEF grades on eCampus and it says you have a 1 or something like that, drop me an email, let me know. This way I'll know to fix it. Good, let's go about 10, 15 more seconds then. And we'll cut that off at like 2 minutes. All right, we're past 2 minutes. And yes, I'm getting, I got rave reviews on this in my previous 2 classes also. So let's remember the definition of isomers, and there's multiple flavors of isomers. Up till now, I think we've really only talked about constitutional or structural isomers, meaning 2 or more compounds that have the same molecular formula, but different connectivity. Which reminds me, I actually thought we were going to do conformations today, which would have been funny since we did that in my 227 classes. But actually for us, conformations are coming on Wednesday. And I pointed this out in the class notes. Your book says that conformations are isomers. That is wrong. Conformations are not isomers. They're just different positions of the same molecule rotated around a single bond. So on that one point, at least I would say, and my colleagues that I've shared it with have been kind of surprised this made it into a textbook. I really should let them know. But no, conformations are not isomers. They do not fall under that definition. So we're looking for a compound that has the same molecular formula, which looks like it ought to be C5H12O, unless I've completely lost it. I think that's right. So, but we want the atoms connected together differently. So you'll notice that A is wrong. That's the same molecule. All we've done is turn it over. So I don't think A is the right answer. What about B? I think we might be okay with B. We got 5 carbons and it's saturated in acyclic and an oxygen. So B looks pretty good so far. C is no good because there's no oxygen, right? It is the right number of carbons, but it's not an isomer. What about D? 1, 2, 3. No, there's only 3 carbons, so we're no good here. And E, I think if you worked it out, it does have 5 carbons, but I would encourage you to figure out its formula. I'm confident you'll find it's C5H10O, not C5H12O. Every time you make a ring or a multiple bond, as it turns out, you got to give up 2 hydrogens in order to do that. So I think the best answer is B. Make sense? And actually, I think I've learned how to grade these on the spot. Whoops, that didn't turn out as well as I'd hoped. But it is what it is. Yeah, I think B is the best answer. Good. Next question. This, I think, will be a little bit easier. Here's the same molecule from the last problem. This molecule is blank. Is that big enough? Yeah, you guys can see. Yeah, you kind of can, unless I go like that. Or even maybe not. Well, that's strange. Yeah, they can. That's interesting. Chat could, but you couldn't. That one, this one's a significantly easier question. I was hoping it came out better anyways. Yeah, you're seeing it from my perspective. Well, you'll notice I've taken care of it. I was wondering about that because in the screen, that wouldn't happen. That's okay. I got to tell you guys, this class is already going 1,000 times better than either of my classes did this morning. The first class, like everything, broke except Zoom. Zoom, thank God, worked. And then about 10 minutes before the end of the lecture, my mic died. So then I went to the next one, and there everything else was fine, but Zoom wasn't working. So this, I can tell, is going to be one of those days. If I can get through it without getting in a car accident, I'll call it a win, you know. All right, we're past 2 minutes, so hopefully this was straightforward. You've got an alkyl group attached to OH. That falls under our definition of alcohols that we gave the other day, right? Remember, a carboxylic acid means you need to have a carbonyl type carbon attached to the OH. But if it's an alkyl type carbon, if it's a hydrocarbon group, then you've got yourself an alcohol. So I think, what does that make it? I think C is the best answer. Yes. Significantly better than the previous one. And like I said, you'll get the remaining 8 points automatically for attendance. And so don't, you know, it probably won't get it right on the Reef website, but I will update it as soon as I get a chance. Good, and I still got to remember to upload these things onto eCampus. We'll do that. Good. So again, sorry about my sloppy handwriting. I'll see hopefully this week, if not then maybe on the weekend, but I'll try to get my hands on a stylus that will then be compatible with this laptop. Good. Let's see. I'm trying to think if there's any other announcements I need to make. Don't think so. I think I'm caught up. I might want to get a few weeks ahead of you again on OWL. So I might try to do that. I'll probably try to do that this week. Oh, and I need to get up some old exam questions for you guys. I'm planning to get that up by sometime tomorrow. I'll do my best anyway. But other than that, I checked my email earlier this morning and I'm not aware of any significant fires that I need to put out. So I think we're in pretty good shape. Good. So basically what we're going to be covering today is, first of all, sources and properties of alkanes. Where do we get them? Where do we get them from in nature? And we can get them from natural sources, as it turns out. We'll talk briefly about reactions of alkanes. I am going a bit out of order from your book, as you'll notice when you look at my class notes. But we'll talk about reactions of alkanes. Spoiler alert, there are very few. Alkanes are pretty inert. There's very few reactions that they will undergo. In fact, I can only think of 2 that alkanes reliably undergo. One of which, combustion, you know already from Gen Chem. So we'll talk a little bit about those just briefly. And then we'll do some review of what? Of non-bonding interactions, otherwise known as intermolecular forces, which you would have covered in Gen Chem, but it's a bit of a sticking point, so I want to at least talk about that a little bit, and then we'll call it a day. I think it's fine if we leave conformations until Wednesday. So that's kind of my plan. So sources of alkanes, where do you get them from? Well, the main sources, as you're probably aware, would be crude petroleum, where we get a lot of other things besides, all kinds of important monomers. We get a good bit of benzene and toluene from crude petroleum. Pretty much all of your straight chain alkanes, probably through, oh, I would imagine it goes well above C20 or even C30 that you can get. But you can find out about steam distillation, which is what they use to separate all the fractions out of crude petroleum. Certainly, I don't care if you memorize any boiling points or anything like that. I don't think that's worth your time. But I can tell you this in terms of what's the word I'm looking for? Well, the treatment or distillation of crude petroleum. I can tell you nothing is wasted. So everything that's all the black stuff that's left at the bottom of the still, when they use steam distillation, that's your asphalt, tar. So nothing is wasted. Everything finds its way into some kind of fuel or something, you know, so nothing is wasted. But certainly your gasoline fraction comes from crude petroleum, you know that. Other types of fuels, airplane fuel, jet fuel, your, what do you call that, diesel fuel, that's all going to come from different fractions of crude petroleum. But mostly that's where we get any of the alkanes we need, whether for fuel or other reasons to make things out of as well. And as I said, and as I think you're aware from Gen Chem, alkanes do not undergo very many reactions. One of them is combustion. And combustion is just the rapid combination of alkanes with oxygen. And the products of complete combustion now, the products of complete combustion are always going to be CO2 and water, no exceptions. So you could write, for instance, butane happens to be C4H10. We could talk about the reaction of C4H10, but I don't know. The reaction of, chat keeps me on my toes. Good, so the reaction of, let's say, butane with oxygen, the products are going to be CO2 and water. Now, there is such a thing as incomplete combustion also, and the book talks about that. These are cases where you get other oxidation products of carbon, like carbon monoxide. And this is a worry in automobiles, right? We need something to get rid of the carbon monoxide for us, because that's super toxic. And there's other things too. We have to worry about oxides of nitrogen, which are also toxic. That leads to photochemical smog and all these other things. So that's largely what the catalytic converter in the muffler is for. It converts a lot of these things to safer byproducts. But you know, balancing these things is usually pretty easy just by inspection. I did these ahead of time, so it looks like, if I'm reading this right, I've got 1 butane, I've got 13 halves O2, and I've got 4 CO2s and 5 waters. And you can double check me, I think I'm right about that. Now, I should just say, in lots of, depending on your Gen Chem book, lots of them are really not real happy with fractional coefficients. I see no problem with them. A simple fraction like that, I think, is just fine. Or if you wanted to just multiply by 2 to get rid of it, 2 butanes and 13 O2s gives 8 CO2s and 10 waters, also fine. I think they're both equally good. So just to give an example of another alkane, if we changed from butane to heptane, which would be C7H16. And how do I know that? Well, because I've memorized the formula for, and I've given this to you in the class notes also, I've memorized the formula for an acyclic, fully saturated hydrocarbon. An acyclic alkane is always going to be of the form CnH2n plus 2. That's always going to be the case. Another way of stating that is if you have a molecule with n carbon atoms, the very most hydrogens you can put on is 2n plus 2. It's not possible to stick more hydrogens on than that. Otherwise, you'd wind up with carbon having 5 bonds somewhere. And as we'll also see, every time you form either a ring or a pi bond, a multiple bond, you have to take away 2 hydrogens in order to accommodate that. So all of your acyclic alkanes are going to be of this form, CnH2n plus 2. Well, 2 times 7 is 14, 14 plus 2 is 16. So that's how I knew. And if you combine that with oxygen, I already have it done, I've got 15 O2s. And I know you did this in Gen Chem. I've got, I think, 7 CO2s. And how many waters? 8. So these are generally pretty straightforward to balance by inspection. You usually don't have to exert, one usually doesn't have to exert oneself too badly in order to balance these. But those are going to be equations for complete combustion. Those will always provide carbon dioxide and water as the only products after a combination of the alkane with oxygen. And again, you can read about examples of what some incomplete combustions might look like. I certainly don't expect you to memorize any of those. But with complete combustion, you'll always get CO2 and water. Make sense? Or any questions? I don't need sleep, I need answers. Well, I generally prefer sleep, but that's just me. Okay, though I can't complain. I got plenty of it last night, so I have nothing to complain about. Good. Now, what about halogenation of alkanes? This is another reaction of alkanes that involves reaction, as you would have guessed, with halogens. And alkanes will react spontaneously with either chlorine or bromine, Cl2 or Br2. Oh, that's another thing from Gen Chem. You remember that chlorine and bromine, those are amongst your, did you do Hankel-Briff elements or Brinkelhoff elements? These are the ones that always exist as diatomic molecules in their most stable state. So Hankel-Briff, hydrogen, oxygen, nitrogen, H2, O2, N2, Cl2, Br2, I2, F2, right? They exist as diatomic molecules in their most stable state. Good. And by the way, if there are any other questions about the combustion, if anyone wants to go over that with me in office hours or something, please don't hesitate. That's what I'm there for. You all got my message about I'm up to 3 days a week, right? Tuesday from 11 to 2, and Tuesday, Thursday from 11 to 2, and Saturday noon to 2. I don't do review sessions. I might have told you guys about this because for some reason, and it's been this way for years. It was this way at my previous school also. I would give a review session and no one or almost no one would come. And the same thing was happening here my first semester. So I've given up on review sessions. I guess it's me. You know, there's something weird about my personality that people aren't coming to review sessions. And I just make sure to give lots of extra office hours in lieu of review sessions. So it looks like that's going to work this term as well. So in a typical halogenation reaction of an alkane, you're going to have some CH bond somewhere in some molecule. I'm just giving a very general definition here. And we're going to treat this with, I'm going to write X2, where X equals chlorine or bromine. It's not you, Dr. Voss. Oh, I don't know about that. You find good humans and terrible humans everywhere. Let me just end this. See, I just need, I just want to get, yeah, I just want to kind of, it's just to adjust things because it's kind of a small screen. Good, so we're going to treat some alkane, so there's going to be some CH bond somewhere in this molecule. The other bonds to carbon can be either to hydrogens or to other carbons. And in the end, we'll talk a minute about what, for a minute late, from an hour or so, what you need in order to make this reaction happen. But in the end, you wind up replacing that hydrogen with whatever the halogen is. A chlorine atom if you used Cl2, or a bromine atom if you used Br2. And the byproduct will be the hydrogen halide. We don't really care nearly as much about that. Oh, I didn't use my lone pairs. Shame on me. It is a sin unto me. There we go, that's better. And in a very real sense, we don't really care as much about that. If you want to write a balanced equation, then yes, that's included there to make it balanced for mass. One thing going forward, and I don't think I need to make a huge deal out of this right now, but one thing you'll notice is about us organic chemists is we are generally kind of sloppy about balancing equations for mass, much more so than what you would have gotten away with in Gen Chem. So sometimes we just won't even mention these inorganic byproducts because we're so much more interested in the organic compound that we get. So this reaction, and we'll learn about types of reactions later too. I would say this reaction in general falls under the class of reactions that you could call substitution reactions. And one type of substitution reaction, all substitution reactions involve basically two bits switching places. And that's the case here. This type of substitution you could call, what's the subscript for Cl? Well, it's X2. So you'll have either Cl2 or Br2, depending on which of the two. This works for both. Does that make sense? It's someone in chat, I think you're asking about that. Well, this is supposed to be oh, Cl comma Br. Yes, that's right. This is a comma. Yep, thanks. It's saying that the X and X2 can be either Cl or Br. Sorry about that. And why not F or I? That's a fair question. It turns out that F2, elemental fluorine, is really ridiculously reactive. And you don't get any controllable reaction when you use F2. F2 just tears the molecule apart, and you get a very complex mixture of products. With chlorine and bromine, the reaction is reasonably controlled, as we'll see. What about iodine, I2? The opposite problem. Iodine does not react reversibly or irreversibly with alkanes. They just look at each other. You certainly don't get any alkyl iodides. But chlorine and bromine seem to be just right. So you can reliably get halogenated hydrocarbons of this type. Now there's a couple of things that you need in order to get this reaction to work. And there's different ways in which these might be written. Your textbook will give you some ideas. The OWL assignment will give you some ideas. One thing that you need basically either light or heat. Or light or heat or a radical initiator. This is what we call a radical reaction. You might have heard of free radicals. They're kind of a bad guy in terms of health, right? Because these things are getting into your DNA and screwing everything up, and it's an issue. So that being said, there are reactions that run using free radicals, using single electron species that have unpaired electrons. And you need to initiate the reaction. One thing that can do it is light. And they might also write H nu if you see something that looks like that. H nu. And that's not a V, that's a Greek letter nu. So if the reason they write that is this is shorthand for E equals, here we go, ignition contributed involving corona. Not sure what that is to do with free radicals, but I don't know, maybe. I'll have to look into that. But this is shorthand for a photon of light, h nu, because Planck's constant times the frequency of the light is the energy of the light particle. So that's why they do that. You can also use heat to initiate the reaction. So it may mention heat or it might say that it heats it up to some stupidly high temperature, 300 degrees or 700 degrees or 80 degrees. It depends just how much energy needs to put in. Or there's also things called radical initiators. Peroxides are pretty good radical initiators. You can use those to initiate the reaction. But you do need something like that. And then there's one other thing that's pretty important about all this. You need to use a large excess of the alkane. Because if you don't, wait, let me make sure everyone understands what I mean by a large excess. I mean that you need to use maybe 10 times or 100 times as many molecules of the alkane as you have molecules of the halogen. There needs to be much more on a mole basis or a molecule basis of the alkane than of the halogen. And the reason for that is if you don't do that, then these monohalogenated products, monochlorides or monobromides, can also go back and find a molecule of the halogen and react again. And you'll get something with 2 halogens, 3 halogens, 4 halogens. You'll get a huge mess. And actually, as we're going to get to in a moment, you might get a mess anyway. But you can at least restrict it to only monohalides, only compounds with exactly 1 halogen, as long as you use a large excess of the alkane. What that will do is it'll make sure you use up all of the halogen, and that the halogen is always in the presence of an excess of the other starting material. And so in the end, you'll just get monohalides of this type and leftover alkane, and then you can separate them. That would be pretty easy to do. What would this look like? What might a typical halogenation reaction look like? Well, the simplest I could think of is to start with the simplest possible alkane, which would be methane. And let's say that we treated this with Cl2. I could just as easily have picked Br2. If you're asked what the major organic product is, again, assuming a large excess of the methane, and maybe this is initiated by light, I could just as easily have put heat or mentioned a radical initiator. You just need something to get the reaction started. So the major organic product would result of swapping out the hydrogen for one of these halogen atoms. And actually, I meant to dwell on that a little bit more before we went on to a particular example. Basically, what's happening is one of the hydrogens on the alkane is switching places with one of the halogen atoms in the halogen molecule. They just swap places. And can you see that's exactly what happened here? You've swapped the hydrogen for one of the halogen atoms, and the hydrogen has then swapped in over here. Instead of a halogen molecule, you get a hydrogen halide molecule, HCl or HBr. We call that a substitution reaction. And later on, as I said, we'll talk about the different types of reactions. But substitution reactions themselves come in 2 flavors. They could be called single displacement and double displacement. This falls under the double displacement category. Did I close reef? Yes, I did. Shoot me an email, and we'll take care of it. Or at least I can drop that later. So it may take a few days to show up properly. Where was I? Oh, so the halogen and the hydrogen are swapping places. And what, oh, does that make sense? Can everyone see how that's exactly what happened? Everyone kind of with me on that? Not really getting any response, so I assume we're okay. Another way to think of this, is, well, then let me put in some colors or something so that you have a visual aid and can see it better. Everyone okay if I draw the halogen molecule like this? And again, mentally swap the X for either Cl or Br. So this is either Cl, Cl, or Br, Br. So far, so good? What I'm trying to point out is that this hydrogen and either one of those 2 halogen atoms, it doesn't matter which, they're the same, swap places over the course of the reaction. Now, the mechanism for how this happens is known. I sure am not going to ask you to draw the mechanism out. It's kind of complicated. but can you see how the red one and the blue one have swapped places? Does that help? And we call that a double displacement reaction. In general, a double displacement reaction is going to take the form AB plus X, well, let's see, AB plus YZ, let's do it that way, gives AY plus BZ. So two of the bits change places. And we'll run into other reactions that are of that type also. This is just one example, but it's a pretty common reaction type. And as I said, we'll go over types of reactions later, maybe in chapter 5 or 6 or something like that. We'll get there eventually. So, and likewise, we can expect the same thing to happen here. If our alkane is methane and we use a large excess and do everything as we're supposed to, well, we would expect one of these 4 hydrogens and one of the chlorines in the chlorine molecule to change places. And so I would expect that you could predict the, whoops, let's go back to black, it's a little easier to see, that the major organic product would be chloromethane, CH3Cl. And if you're asked what the inorganic side product is, or if you're asked for a balanced equation, then also mention that HCl is formed. And I guess at least in the organic portion, let's, at least for now, be careful with our lone pairs. So, and this again points out the reason why we need to use a large excess of our alkane, because otherwise, this chloromethane molecule can find a chlorine molecule and make CH2Cl2, and then do it again and make CHCl3, and even in principle do it again and make CCl4. So in order to avoid that, we're always careful to use a large excess of the alkane. So that's one example. What if instead we used cyclohexane? I'm just giving you examples of what these might look like. Let's say you're asked what the major product is of cyclohexane and bromine, using a large excess, of course, of the cyclohexane. And again, this can be initiated by light or by heat. I don't know exactly what the temperature would be. If I had to guess, I would guess it would be in sort of the 100 degrees Celsius area. I would think that would do it. Well, the cyclohexane, this is C6H12. Each of those carbons is a CH2. And you can pick any one of those 12 hydrogens. They're equivalent for us here. And so you'll just replace that with a bromine, and that will be your major organic product. So it doesn't matter where on the 6-membered ring you put the bromine. All of those positions are equivalent for us. Right? You can turn that molecule whichever way you want, and you'll get the same thing. And then if you're also asked for the inorganic side product, that would be HBr. Hydrogen bromide. I want this to go to everyone. Good, so these are just examples. And again, as long as you use a large excess of the alkane, there's no problem. That's going to be your major organic product. Where are we at? 3:30. I have until 3:45. Looks like this is going to work out just about perfectly. We can save confirmations until Wednesday. Questions so far then? Well, actually, it's a little bit more complicated than that. How do you make sure it's a large excess? Well, just when you mix the things together, if you were doing this in real life, you would just, I don't know if you guys, it's a good question in chat. How do you make sure it's a large excess? Well, you do that calculation before you do the reaction. That was all that stuff in Gen Chem you all enjoyed so much about stoichiometry. So you just make sure that for every mole of Br2, you're using maybe 50 or 100 moles of the alkane. And the question is about these. I would say the way it's drawn here would get full credit, but also remember your exams are multiple choice. So a lot of those things are going to take care of themselves. Do be careful with OWL. Make sure that you're following the directions. Sometimes they'll be picky about lone pairs, sometimes they won't be. Sometimes they'll ask you to consider different stereoisomers, which we'll eventually get to. Other times they'll say, don't worry about stereochemical issues. So you need to read the questions carefully, but we're going to do just pure multiple choice format, which I don't love, but I think under the circumstances, I have very little choice with this many students, especially since I don't have a TA or anything. Okay, where was I? We were doing this one. Oh yeah, so you just run your calculations and just make sure that for every 1 mole of your halogen, you've got, I don't know, pick a number, 50 moles, 100 moles, 200 moles of your alkane. And then you get that much of the material and you toss it in when you mix them together. So that's taken care of before you do the reaction. You have to run the numbers and make sure that you've got enough of an excess of the alkane. But I've never done a reaction like this, but if I were going to do so, I would be that extreme at least. Well, of course I would try to, I would probably be best served by looking up a paper where someone actually, a journal article where someone did it. But if, apart from that, if I had to take a wild guess, I don't think 100 mole equivalents is too much. 50, I would think, certainly is not. I don't care if you know that, but you just should be aware that you need an excess of the alkane. Otherwise, you could get multiple halogens and mixtures of different products. And that gets me into saying, well, it's actually, unfortunately, a little bit more complicated than that. Because I've been picking alkanes like methane and cyclohexane, where all of the hydrogens are the same. And so there's only one possible product. Ethane, by the way, would go the same way, CH3, right? All 6 of those hydrogens are the same. So if you treat it with chlorine, you get chloroethane, and if you treat it with bromine, you get bromoethane. Those are the only possibilities. What, though, if we started with propane? Well, now, not all of these hydrogens are the same. These 6 on the ends are the same as each other, this CH3 and this CH3, but you've got this CH2 in the middle. Those 2 hydrogens are different from either of those 6 hydrogens. How do you know? Well, let's say we went ahead and mixed this with chlorine. And again, assuming a large excess of our alkane. And let's say we initiated this with light of the appropriate wavelength, H nu for light. Well, then actually, I think you'll agree with me, when you go to replace a hydrogen with a chlorine, there's 2 possible products. And actually, I think we can already name them. One of them would be 1-chloropropane. The other one would be 2-chloropropane. And I think you'll agree with me, those 2 compounds are different. They're isomers. And yes, you will still get the HCl. That's always going to be, the hydrogen halide is always going to be your inorganic side product. The phrasing of the question will tell you whether you need to put it or not. And by the way, OWL is especially weird about inorganic side products. I've seen questions where they want you to include a box with like Na+ in it, because there's some sodium salt that's the product. I think it's ridiculous. I don't see myself doing that to you guys. But read the directions carefully, because they will vary in terms of what they want. But there's 2 different organic products, because if you take let me get a different color. If you take any of these 6 hydrogens, there's 3 here and 3 here, and replace with a chlorine, you'll get this product, because all 6 of those hydrogens are the same. Replacing any one of those 6 hydrogens with a chlorine gives you 1-chloropropane. But what about these hydrogens over here? Those 2 hydrogens are different from this one. And the way you can know that is that when you replace one of them with your halogen, you get a different compound. And I would expect that you guys can look at these 2 and tell that they're different compounds. They're isomers. They're both C3H7Cl, but they're different from one another because they're connected differently. And the way you can tell that they're connected differently is that here we have a chlorine that's, or rather a carbon that's attached to a chlorine and a CH2. You've got CH3, CH2, CH2Cl. I don't see any CH2Cls here. This carbon here is attached to just 1 hydrogen plus the 2 CH3s. There's no CH2Cl, so the connectivity is different. I would say if you want to know how to see whether they're different or not, and you're having a little trouble with these line angle drawings, well, then just draw it out in condensed form. I would expect you to be able to go from this to CH3, CH2, CH2, Cl. Remember how we defined every sharp corner or point is going to be a carbon. So does everyone see how I went from this to this, that they're the same thing? And again, you don't need, it's not mandatory for you guys to use line angle drawings. If you'd rather draw them like this, that's fine. It's not mandatory for you to use these. All I ask is that when you see line angle drawings, you understand them. That's the main thing. You draw structures in whichever way is the most comfortable for you. I think you'll find before too long, probably have found already, that unless you abbreviate at least in some sense, it gets very tedious very quickly. C, H, 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 C, H, you know, takes forever. So I think you'll gravitate towards at least condensed forms, maybe for smaller molecules. And then once you start getting up to even 4 carbons, 5 carbons, we start to use line angle drawings. I tend to use a mix of line angle drawings and condensed forms. But that's almost a personal preference thing. Everyone's a little bit different. Everyone has a slightly different style in drawing chemical structures. Good, so my point here is that with many alkanes, there are multiple monohalogenation products that are possible. And you'll get a chance to practice that on OWL. They'll probably pick something worse than propane. So what we're saying here is even with a large excess of the alkane, using a large excess only makes sure that we just get compounds with one Cl in them, with one Cl or Br, that is, with one halogen. We can call them monohalogenation products, or monochlorination in this case. Again, there's a lot of words here. One of my colleagues at my previous school, interesting guy, he had taught high school chemistry for something like 35 years, and then took early retirement from that and joined the faculty at the college that I was at for, I guess he came about a year before I did. So he kind of knew what he was talking about when it came to teaching chemistry. But he would say that in a semester of a typical Gen Chem or organic chemistry course, you learn as many new words as in 4 years of a high school foreign language. And I tend to believe it. I wouldn't be surprised. In any case, so even if you use a large excess of the alkane, that just makes sure that you get only monohalogenation products. But there's no way to stop getting mixtures of monohalogenation products. Now, if your alkane is methane, you're in good shape. There's only one possible product, chloromethane or bromomethane. Ethane, same thing. Cyclohexane, same thing. But as soon as you get a little bit larger, you get this possibility, and there's no stopping it. Now, how much of the 1-chloropropane compared to the 2-chloropropane do you get? That's getting a little bit deep into the weeds. I don't think we need to worry about that. I wouldn't expect you to tell me it's so many % of this and so many. I mean, I wouldn't even know myself without the experimental data. But I would expect you to be able to tell me that both of these products are possible. I don't care if you can guess as to the relative amounts. Actually, the answer might surprise you. But that's getting a little deeply into the weeds. For those who are really curious, you might think that you would get more of this because there's 6 of this type of hydrogen and only 2 of the type of hydrogen that you get. So you might expect it would be 3 to 1 or 6 to 2. That's a good guess, and it would turn out to be wrong. I don't know what the exact amount is that you would get. One could look it up, but I bet you'll find that you get a lot more of this than you would have expected. And that is to do with the mechanism of the reaction. Like I said, I think that's getting too deeply into it. I did say that we are going to avoid some detail, a fair bit of detail in this class. That's one thing that I don't see any benefit to your concerning yourself with. So, I mean, like I said, with a question like this, you could just predict these are the 2 possible products. I'm happy with that. I don't expect you to speculate as to the relative amounts. And like I said, you'll get to practice that on OWL. So you'll get lots of examples of questions like this. You'll see how they're phrased. You'll see what sort of answers get credit. I think there's plenty of opportunity there. Good. So I think that at least gives you, at least that should be enough to get you started on this topic. For our final 5 minutes today, I just want to remind you about the intermolecular forces that explain the properties of most molecules. And one of the reasons, by the way, that alkanes are pretty low boiling compared to molecules of similar molecular weight that might have oxygen or other atoms in them. And that is to do with intermolecular forces. And you covered that in Gen Chem. I think the major intermolecular forces you covered were hydrogen bonding, surely. That one's pretty important, so I'll spend our last few minutes on that. You probably also talked about dipole-dipole forces, and a third intermolecular force goes by a few different names. You might have called it van der Waals forces. You might have, not van der Waals, van der Waals, there's an L in there. Or you might have called it London dispersion forces or just dispersion forces, same critter. Both of those names refer to the same thing. And that's the type of intermolecular force that you have when you have basically a completely nonpolar molecule, like an alkane, or like a Cl2 or Br2 molecule, or like a noble gas atom, that's a completely nonpolar species. But hydrogen bonding is somewhat important. That's gonna come into play when we start looking at the properties, especially of oxygenated compounds. And hydrogen bonding, I'm just going to put H bonding over here. Hydrogen bonding is an intermolecular force that comes about when you've got hydrogen directly bonded to one of three elements, either to oxygen or to nitrogen or to fluorine. And of course, if you bond hydrogen to fluorine, well, you're done. Both hydrogen and fluorine can only form one bond, so the only molecule that obeys that, or that follows that description is HF, hydrogen fluoride. But of course, with oxygen and nitrogen, we've got other bonds attached. So as long as you have hydrogen, now it has to be directly attached. Please don't miss that part. It has to be directly attached to the oxygen or to the nitrogen to experience hydrogen bonding to its fullest effect. And what we find in species with hydrogen bonding is two or more molecules of the same species will approach each other and have an attractive interaction. You probably mostly used water. I'm going to kind of pretend maybe we have an alcohol here. So here's a molecule of an alcohol. And what we find is that another alcohol molecule will come along, and there'll be an attractive force. And this is the really important thing that you understand. You're talking about different molecules, but there's an attractive force between the hydrogen of one molecule and the oxygen of another molecule, more specifically, the lone pair of electrons on that oxygen. And that kind of makes sense. This oxygen can really be almost considered to have a partial minus charge on it. It is these two lone pairs of electrons. There's high electron density there. Plus you've got an electronegative atom. So there is a good bit of electron density sitting on the oxygen. And where does it get the extra electron density from? Well, the hydrogen for one, and whatever the carbon is that's attached over here for another. So there's gonna, if anything, be a partial plus charge on the carbon and on the hydrogen. So this electron-rich oxygen and this electron-poor hydrogen are gonna be attracted like little magnets, because that's exactly what they are. And that's the nature of hydrogen bonding. So please be aware hydrogen bonding is a different thing from covalent bonds. There is not a covalent bond here, but there is an attractive force. And that attractive force is a lot weaker than a covalent bond, but it is something that needs to be disrupted or pulled apart in order to separate these molecules one from another. In other words, to make them go from the liquid state into the gaseous state. And so that's why your oxygenated molecules, your alcohols, water, even ammonia, these things have much higher boiling points than you would otherwise expect based on their molecular weight. And I don't expect you to memorize any numbers here. That's not the point. But I would like you to review about intermolecular forces. And again, I think hydrogen bonding is going to be one that we use a fair bit. So, but the main thing to remember for hydrogen bonding is to look for these three types of bonds, which really turns out to be those two types of bonds. You need hydrogen directly attached to either oxygen or nitrogen or fluorine, but that set includes only HF. These include many other molecules. As long as you have that going on, you've got the potential for hydrogen bonding. Otherwise, not so much. And with that, I'm out of time. So I will see you all on Wednesday, and we'll get into conformations. But again, please do note that your book is wrong. It says that conformations are isomers. They are not. Conformations are not isomers. Other than that, have a great day. See you all Wednesday.